A limit is the value that a function or sequence approaches as the input approaches the same value. Limits can be used to determine continuity, derivatives, and integrals. Now we'll look at some basic limit laws. First, we'll look at this problem, as we have the limit of 5 as x approaches 4. In this problem, we do not have any variables, so the number right here, 5, that is left, is our answer. In the next problem, we have the limit of x as x approaches 4. We can use direct substitution to find our answer. We plug in 4 for x, and we get the limit of 4, which is equal to 4. Next, we have the limit of x squared as x approaches 4. We can use direct substitution to find this answer, and we plug in 4 for x, and we get 4 squared, which is equal to 16. In dealing with polynomials, to find the limit, you will use the sum and difference formula. Here we have L is equal to the limit of f of x as x approaches c. Here we have k is equal to the limit of g of x as x approaches c. The sum and difference formula states as the limit of f of x plus or minus g of x as x approaches c is equal to L, the limit of f of x as x approaches c, plus or minus k, the limit of g of x as x approaches c. Here, in this problem, we have the limit of 6x squared plus 5 as x approaches 2. We can take the limit of 6x squared as x approaches 2 plus the limit of 5 as x approaches 2. We can use direct substitution for this problem, and we will get 6 times 2 squared. And here we have no variable x, so we just have 5. So plus 5. 2 squared is 4, times 6 is 24. Plus 5, and our answer is 29. Limits can also be solved by factoring. Here in this problem, we have the limit of x squared plus x over x as x approaches 1. We can simplify this equation right here into x times x plus 1 over x, and have the limit as x approaches 1. Here, both x's will cancel out, as x over x is 1, and we can directly substitute the 1 in to the equation, and we will get 1 plus 1, which is equal to 2. And that is your answer. Now we're dealing with rational functions. In this limit here, we have x squared plus x plus 4 over x plus 1. Since we can't factor, we will have to direct substitution. You will plug in 1 for every x. So 1 squared plus 1 plus 4 over 1 plus 1. This simplified is equal to 6 over 2, which is equal to 3. And that is your answer. Dealing with trig identities. Here we have the limit of sine x as x approaches c. To find the answer, we just plug in c to the equation, and then we solve. Most trig identities or trig limits can be solved with direct substitution. Here in this problem, we have the limit of x times cosine x as x approaches pi. To solve this, we'll use the product rule. First, we'll take the limit of x as x approaches pi times the limit of cosine x as x approaches pi. Then we solve. So here we can use direct substitution and we just get pi. And here we have the limit of cosine x as x approaches pi, and we get cosine pi when we direct substitute. And then cosine of pi is -1, so we just get, the answer here is -pi. For product rule, we have the limit of f of x as x approaches c is equal to L, and the limit of g of x as x approaches c is equal to k. With the product rule, it states that if you have the limit of f of x times g of x as x approaches c, you will take the limit of L times the limit of k. So for this problem here, we have x times x plus 1 as x approaches 1. We can take the limit, or we can simplify by taking the limit of both. So we could get the limit of x times the limit of x plus 1 as x approaches 1 here and x approaches 1 here. So we direct substitute here and we get 1. And we multiply by this limit and we direct substitute in there, we get 2. And 1 times 2 is 2, and that is our answer. Now we are dealing with quotient rule. Again, we have the limit of f of x as x approaches c is equal to L, and the limit of g of x as x approaches c is equal to k. Quotient rule states that the limit of f of x over g of x as x approaches c is equal to L over k. Here in this problem, we have the limit of 8x squared over 3x as x approaches 2. To simplify this problem, we can take the limit of the top and the bottom. So we will take the limit of 8x squared as x approaches 2, and we will divide it by the limit of 3x as x approaches 2, and we can use direct substitution to find both of these answers. And here we plug it in, we get 8 times 2 squared over 3 times 2, and that gives us 32 over 6, which simplified is equal to 16 over 3. Here we are dealing with power rule. For power rule, we will start off with the limit of f of x as x approaches c is equal to L. Power rule states that the limit of f of x to the nth power as x approaches c is equal to L to the n. Here we have a problem, the limit of 3x to the 5th as x approaches 2. First, we will simplify this problem by taking the limit of 3x. So we have the limit of 3x as x approaches 2. And we direct substitute 2 in there, and we will get 6. And we will take that answer and put it to the 5th. And we will get 7,776. And that is our answer.
As is the case with all limits where x approaches infinity, the only thing that matters is the highest power in the numerator and the denominator. Therefore, in this equation, the plus 10x and plus 4 in the denominator have no bearing on the results. So the equation could be rewritten as x cubed over x squared, which can then be algebraically simplified into just x. At that point, you just plug in the infinity, which gives you the limit of infinity, but that's not an acceptable answer, so you instead write the limit does not exist because it is increasing without bound.
Bound.
In an equation where the highest power in the numerator is the same as the highest power in the denominator, all following values in the expression don't matter. So in this example, the 3x plus 8 in the numerator and the plus in the denominator have no bearing on what the limit is. And instead, you just look at what's left. And since you're dividing something by itself, the limit will come out to be 1 regardless of what you put in. Since in this case it's infinity, you would plug in infinity, but it still comes out to 1. So in this example, similar to the first one, which was 1 over x, the denominator has a higher x value than the numerator does, meaning this could also simply be expressed without these unnecessary, unwanted terms in the numerator. Since the denominator has a higher power than the numerator, the value will always be approaching 0, because no matter what you put in, the denominator will be another order of magnitude higher than the numerator. So this comes out to equal 0. Some equations, like this one, might look like they can be solved by simply plugging in the number you're given, but that's not the case. Because all limits, unless indicated otherwise, you have to check what happens as the value is approached from both the left and the right. And in this equation, you can do that by using values, simple values in our case, that are above or below it. So we'll use 3 for below it or to the left, and 5 for above it or to the right. First, we'll plug in the 5. So our equation become 5 minus 4 square rooted, which can be turns into a 1, square root of 1, rather simple. And from the left, it would be the square root of 3 minus 4, which turns into the square root of negative 1, which, for our purposes, does not exist. So it does not work from both sides, and therefore the limit will not exist, because the left limit does not equal the right limit.
For the conjugate rule here, what we have to do, because if you plug x in directly, you're going to get a 0 in the denominator, and that's a vertical asymptote, and that's not happening. So you got to multiply it by the opposite here, which is going to be square root of x plus 2 over square root of x plus 2, which that's going to give you, because I don't want to show all the in-between stuff because everyone knows how to FOIL, 1 over square root of x plus 2. And then when you plug that in, you're going to get 1 over 4.